Hello. In this last lecture in this series, we'll be looking at Poisson distribution. So the Poisson is also a discrete distribution, and here the Poisson counts the number of occurrences of a phenomena in a fixed interval. Now the fixed interval could be a time period, a fixed area, or fixed volume. Volume is what we use generally as a generic measure of space of some kind. And so, as before I said, this is a counting process similar to binomial. Examples are typically the number of telephone calls in some time interval, the number of cars queued up at a traffic light in 1 minute, say, the number of arrivals at a toll bridge per minute, the number of times a printer breaks down in a month, paint spots on a new car, the number of paint spots or other such deformities, number of sewing floors. You might take a look at the number of tumors, not nice things, the number of tumors, say, in a liver cell, in a liver, or those kinds of things. So this is where Poisson comes. Now, the important thing is the assumptions. The occurrences are independent of each other. So two cars coming to the lights will be independent of each other. And the next is you can't have two occurrences at the same location. So I can't, for example, have two cars at the same place coming in at the same time in the traffic lights. And the mean number of occurrences is fixed, or the volume is fixed. So if I look at the minute interval when I'm looking at the number of cars banking up at the traffic lights, then the number of cars that come in a minute are the same for every minute I'm looking at. Comparison with binomial, often people confuse, or students confuse binomial and Poisson. The difference here is that binomial has a fixed number of trials. Poisson doesn't. Binomial has a probability of success and a number of trials. Poisson doesn't. Poisson just tells you the mean number of occurrences. Binomial has two possible outcomes. Poisson doesn't. And binomial can take only values between 0 and n. Poisson can keep going on forever, in principle at least. So be careful not to confuse the two. So the probability mass function of Poisson is given by this formula. Its probability that k takes the value k is e to the negative lambda. So lambda here is the Poisson mean. We write x as phi mu. This means x has the distribution Poisson with parameter lambda here. The mean is lambda. So its probability of x taking the value k is e to the negative lambda, lambda to the power k, and k factorial, where k is 0, 1, 2, 3, and so on. The cumulative, of course, is the sum. Again, not so interesting for us because we can just add the probabilities in the table or look up something like R. Now, the question here is for those who have done more mathematics, do the probabilities add to 1? If I add all these up, or all the values of k, do I get 1 from there? You can ask me if you wish, interested. Some examples over here. So, a real estate agent sells 1.5 houses per day on average. So, of course, in a given day, he or she won't sell 1.5 houses, but this is an average. Assume the sales are Poisson, and of course that means we're assuming they're independent of each other. What's the probability of selling exactly 2 houses on a day? So here we're looking at 2 houses on a day. So we want to define ourselves, first of all, a random variable. So I'm denoting x as the number of houses sold in a day. X is Poisson. The mean is 1.5. I want x equals 2. My formula says e to the negative lambda. So it's e to the negative lambda, the mean over here. Then the mean to the k, 1.5 to the k. So it's e to the negative lambda, lambda to the k over k factorial. So lambda here is my 1.5. So it's e to the negative 1.5. It's 1.5 to the power k, which is 2, and then 2 factorial. That comes to 0.2510. Next part says no houses sold. That's x equals 0. Again, the same formula. E to the negative 1.5, 1.5 to the 0, and 0 factorial comes to 0.2231. Next part says probability of selling at least 5 houses on a day. That's at least 5 means x is bigger than or equal to 5. So again, the way we think of this is going to be as the complement. So it's 1 minus probability of x less than or equal to 4. So I go to my R command again. and I go distributions. This is discrete and it's Poisson, and I'm looking at tail probabilities. The variable value here, I wanted x less than or equal to 4. So that's what I put in there. And the mean is 1.5. That's 0.98142, so on. What did I get this? Check again. 0.98, oops, sorry, 14. And that's 1 minus that. That's 0.0186. More than 5 houses. So this is more than 5. Actually, sorry, I can see I got it wrong over here. No, that's fine. Bigger than or equal to 4. More than 5 is 1 minus probability of x being less than or equal to 5. So I don't want 5, I want more than 5. So this means I take off the 5 part over here. And so if I then again do this using my R commander. So same idea as before. Distributions, discrete, Poisson, I want tail probabilities. Now this becomes a 5 instead of a 4. And now I've got 0.9955. So if I'm selling on average 1.5 houses, I'm not going to sell 5 or more than 5 very often. So here the question part is probability of selling exactly 5 houses in 2 days. So now my periods changed from 1 day to 2 days. So my random variable y will denote the number of houses sold in 2 days. So then y will have again a Poisson distribution, but the average for 1 day was 1.5. So for 2 days it's going to be 3. Scales in the usual fashion. I want here exactly 5 houses. I want probability of y equals 5. So that's going to be e to the negative lambda, so it's e to the negative 3. The lambda to the power k, so that's 3 to the power 5 over 5 factorial. You can calculate that with a calculator. I'll use R again. So I'm looking here distributions, discrete, Poisson, and I want here Poisson probabilities. The mean is going to be now 3. And so it's listing probabilities for me. Well, I want probability of y equals 5 here. Yeah? So 5 over here is 0.1008. That's that problem solved. Mean and variance, well, we know the Poisson mean is just mu, so if I've got Poisson lambda, that's the mean. It works out that this is also the variance. So this is one distribution where the mean and variance are the same. And the standard deviation, of course, is going to be the square root of variance, so that's square root of lambda. So we'll catch up by doing more problems in lectures, and we'll see some more tricky situations in lectures. That finishes the lectures for this chapter. Thank you.